I would like to introduce our first speaker. Our first speaker is Samuel Farrens, and he is going to speak about PySAP from Galaxies to Brains and beyond. Samuel is from CEA Paris-Saclay. Samuel, you've got half an hour, and I'll give you a 10-minute warning.
Okay, hello everyone. Thank you very much for taking the time to listen to my talk today. I'd like to start by giving a warm thank you to the organizers for inviting me. It's a shame that we're not all together in Granada, but I've given you a kind of virtual Granada behind me. But I would like to just point out how impressed I am by the organization of this event so far, and especially during a pandemic. So I could tip our virtual hats to the organizers. So today I'm going to be talking to you about PySAP under the umbrella of cross-discipline projects. So let me get started. So I'm just going to spend a second to explain where I work, and then I'm going to give you a little bit of background about inverse problems in order to kind of motivate why PySAP exists. Then I'll get into explaining what PySAP is and some of the applications where PySAP is being used, and then just leave you some closing thoughts. So where I work at the CEA, so that's the French Alternative Energies and Atomic Energy Commission. So I work in the division of fundamental science in a lab called Cosmostat, which specializes in cosmology, signal processing, and machine learning. I also spend part of my time at Neurospin, which is a neuroimaging center right across the road that specializes in MRI, cognitive neuroscience, image processing, among other things. So the overlap being on the image processing side, we've kind of found that we're using many of the same mathematical tools, and the applications are different, but the ideas behind them are quite similar. And so kind of sharing our knowledge and expertise will help each other improve. So I'll just take this slide to point out that all of the links that you will see popping up on the top left-hand corner will be clickable in the PDF version of this slide. So feel free to revisit these and find all the resources later on. Okay, so let's get into the background. So I'd start by defining what an inverse problem is. And the easiest way to do that is to define the opposite. So if we start from a cause and produce an effect, that's something we would define as a direct problem. So conversely, an inverse problem would be inferring a cause from an effect. And in a more scientific context, it's more convenient maybe to change these words to model and data. So if you observe or acquire some data and then infer an underlying physical model from that data, you're in a sense solving an inverse problem. So more concretely, we can define a linear inverse problem as an inverse problem that can be modeled as the following linear inverse problem in a linear algebraic form. So, we have our data that we observe as a vector y, the model that we want to recover as a vector x, and then some matrix H that transforms between the two. And in addition, you might have some additional noise components on top of this operation. So a specific example that we could think of would be for images. If we have an image, for example, of this cute raccoon, the model vector for this would be simply the pixels that make up this image. The data vector would be the pixels that make up the observation we recover of this image. And then H, in this case, would probably be the instrumental response or point spread function of whatever instrument we use to capture this image. So the inverse problem that we'd want to solve is, given this image and presumably the knowledge of the point spread function of our instrument, can we recover the original picture of the raccoon? So in simple words, yes, if this was a noiseless image, we could do this analytically. Unfortunately, if there's even a tiny amount of noise in here, trying to solve this analytically, which in this case would simply be doing a Fourier deconvolution, so dividing this image by this PSF in Fourier space and then converting back to direct space, would blow up the image. And the reason for that is that the tiny amount of noise contributes to high spatial frequencies to the reconstruction that just destroys everything. So in a situation like this, the problem is ill-posed. And so I'll just define what ill-posed means. So for a well-posed problem, we need an inverse problem for which a solution exists that's unique and that the behavior changes continuously within initial conditions. So by contrast, an ill-posed problem is one that one of these conditions is not satisfied. And in the previous example, specifically, that operation matrix, the convolution with the PSF, is ill-conditioned, meaning that its behavior does not change continuously with initial conditions, meaning that a small change like noise completely destroys the problem. So in order to solve a problem like this, we need to add some additional information. And in the world of inverse problems, this is called regularization. So another way to think about this would be a prior. So if we use some prior knowledge of the signal that we want to recover, we can try to favor good solutions, and good meaning whatever metric you are trying to use to establish the quality of your reconstruction. And a way we can think about this is the regularization is preventing overfitting to the data. So I could spend all day talking about all the different regularization techniques that you could implement in an inverse problem. But today I'm just going to mention one, which is sparse regularization or sparsity, which is the most well represented in PySAP, for example. So just to define what we mean by sparse. So a sparse signal, we can take any data vector x, and we can decompose it into a dictionary phi and a sparse representation alpha. So phi is an operator that converts from our direct space to our sparse representation. One very common example of this would be the Fourier transform. So if, for example, we had a discrete sine curve and we take the Fourier transform of that signal, we get the frequency of this, for example, this time series. So what we want to notice here is that in the direct space, we have many points that we need in order to describe this signal, whereas in the Fourier space, essentially all we need is one point, which tells us the frequency of that curve. So this is a sparser or more condensed representation of the signal, and this is an inherent property of the signal. So if we know a priori that the signal we want to recover is sparse in this space, then we can favor solutions that have that same property. So in a sparse regularization problem, we're going to define an optimization problem where we have a data fidelity term, which assures that the solution that we find fits the observation well, but we're also going to impose that it has this sparse property. And what we can kind of think of is then what we have is a kind of convex space of possible solutions at which we want to find the global minimum. And this sparsity term is restricting that space to solutions that have this property. So using this kind of prior knowledge. So that's the basic idea. And I hope in this section, at least, you've come away with understanding what the definition of an inverse problem is, why you might need to use regularization, and why sparsity might be a good source of regularization for certain problems. So now we can talk about what PySAP is. So PySAP was created under the COSMIC project, which was a project internally funded by CEA, which was a collaboration between Cosmostat and Eurospin. So I think this is a very nice example of an institute putting money where, out to fund a cross-discipline project, which is, something I think we're starting to see a bit more of, but we probably need to start thinking more about in the community. Of course, there are many people who have contributed to PySAP in different ways. So here I've listed some of the main people. So those in blue are kind of still actively involved with PySAP, and those in red were in the past. So PySAP itself. So PySAP stands for Python Sparse Data Analysis Package. So now that you have at least a basic understanding of what sparsity is in terms of inverse problem solving, the PySAP is essentially a toolbox that allows you to solve these types of inverse problems. And it's made up of three main components, which I'm going to describe individually. So just before moving on to that, following yesterday's very nice talk on AstroPy, there is actually a paper on PySAP that we use as the main source for referencing PySAP if people were to use it in the future. And we spent a lot of time in trying to make some decent documentation that can still be improved, I'm sure. So let me get into explaining what all of these components are. So sparse 2D. So we talked about at the beginning what sparsity was and what this phi is in terms of that time series was a Fourier transform. But in fact, this can be any sparsifying dictionary that gives you a sparser representation of your signal. So in practice, this concerns a whole series of wavelets that could be for one-dimensional signals, two-dimensional images, three-dimensional data cubes, and so on. And having a suitably large library of these dictionaries enables you to solve a vast array of different problems. And that's exactly what Sparse 2D is essentially a library of wavelet transforms in various dimensions for solving inverse problems. So Sparse 2D was written in C++. And what PySAP does is provide full Python bindings to these libraries so that you can use them in a fully Pythonic way and allow you to use them in combination with other PySAP tools. So one specific example of a wavelet included in Sparse 2D is the Starlet Decomposition, which is a isotropic undecimated wavelet transform. And this has been demonstrated in various papers to be extremely well suited to astronomical images. So for example, if we take a galaxy, we can decompose it into high spatial frequencies and then the coarse grain features of the galaxy. And the nice feature this decomposition has is that if we simply add all of these different wavelet scales together, we recover the original image. So it's not only a good representation, it's also an easy one to use. So once you've kind of established what your problem is and maybe even identified an appropriate wavelet, you still need to use an optimization algorithm to solve your inverse problem. So what ModOp does is provide a library of different optimization algorithms that have been built in a particularly modular way so that they can be combined with various different proximity operators and linear operators in order to solve a kind of vast array of different types of inverse problems. And we've put a lot of effort into the API documentation such that it's should be for the user easy to understand how to use these different algorithms in combination with these different tools and all the options that can be provided to them. So let me just give you one example. So this is an example of the Condé primal dual splitting algorithm. So if you're like me, you might see something like this and the first time be a little bit terrified. But what we've tried to do in ModOpt is kind of break this down into different pieces so that they can be used in a modular way. So we can take an algorithm like this and then ModOpt will allow you to define a gradient, essentially, which is the derivative of your data fidelity term. A proximity operator, which is kind of like a proxy for the derivative of your regularization term. You can input one of your dictionaries, so from Sparse 2D, one of your wavelets. And then you'll be able to use this algorithm to solve your particular inverse problem. And so that's kind of the whole philosophy behind ModOpt is kind of making this like a little toolbox where you can stick in all of these different pieces together in different algorithms for different problems. So combining those two things, so Sparse 2D and ModOpt, we kind of come to what we would think of more as the end user product, which are the plugins. So this is where we take, a specific algorithm with some specific setup and hyperparameters combined with some specific dictionary in order to solve a problem in a given application. So we have a plugin for MRI, Astro, and there's one in development for Electron Tomography as well. And the idea being is that this will just give the user the direct access to the solution, let's say, to a specific type of problem. Like I want to deconvolve a galaxy image, I stick in my data and get out the result directly through this plugin. So the plugins are managed in separate repositories, but are fully integrated into the core of PySAP. So once updates have been made in these repositories, they're once and released, then they can be accessed directly in PySAP. So the end user only needs to install PySAP. So an important point to note about the plugins is that you can make your own. We have a template that is available on our repository where you can simply fork this and create your own plugin for maybe a new imaging domain or something that we haven't thought of. And then you could submit a, let's say, plugin review request, and we will see if we can integrate that directly into core PySAP so that it's distributed to the end users in the community. And so next, I'm going to talk to you about applications. But just before then, I just want to point out that one of the main things that we're very keen on for in the PySAP team is open source development, and trying to make this as easy as possible to contribute to. So we have written fairly extensive contribution guidelines to try to make it as easy as possible to understand how to contribute to PySAP. It can always be improved. We also have a code of conduct so that we try to make it a safe and inclusive environment for everyone to feel comfortable to contribute to PySAP. And we also have various issue templates to try to make it easier for people to report issues that they notice with the code or suggest new ideas. Okay, so hopefully at this stage you understand at least what the idea is behind PySAP, where you can get it. Let me just explain now what people are using PySAP for. So one of the things at Cosmostat that we're really interested in is weak gravitational lensing. So for those of you who may be not familiar, weak gravitational lensing is the distortion of background images, in particular galaxies, by foreground matter, and which causes a kind of shearing or squishing of galaxy images. And so by measuring the shapes of galaxy images, we can statistically infer the amount of dark matter, for example, in the universe, but also how this effect evolves over time. We can also learn about dark energy. So this is something very exciting in cosmology, but we have a couple of issues. So one is that we need to be able to measure the shape of a galaxy, like the one you see here on the left, from an observation like you see on the right. So if we go back to our initial raccoon example, one of the things we could try to do is deconvolve the PSF, so the distortion of the instrument and so on, from our image, and also denoise it at the same time, so that we can try to infer only the distortion of that image caused by gravitational lensing. So this is just an example of a deconvolution problem that I implemented a few years ago using sparsity, and that is now directly available in the PySAP Astro plugin. So that you could take a similar data set and stick it into PySAP and get the same sort of results that we're recovering. The idea for this particular paper was that we have an anisotropic PSF that varies across the sky, but it was assumed that you knew what the PSF was. So in reality, that's often very difficult to know. So there's another PhD student at Cosmostat who's working on a multi-CCD point spread function modeling using a parametric method called MCCD. Where he takes stars in the field and gets an estimate of the PSF from those stars. Stars being like point sources kind of give us a good estimate of the point spread function. He can use all of the stars in the field simultaneously to kind of build a model of the PSF, and then compare that to stars for which were not included in that modeling, and you can see that there's very little residual, if any, from his model, showing that it's a pretty good representation of the point spread function. And so this MCD algorithm was built using PySAP as a backend, so using the various dictionaries in Sparse2D and the algorithms in ModOpt. So moving beyond astrophysics, we also have the biomedical domain. We have the concept of compressed sensing. So the problem here that one is trying to solve is that in medicine, doctors need to have high resolution images of, for example, the human brain in order to identify, certain conditions, diseases, or what have you. And in order to get those high resolution images, you need to fully sample or, very conclusively sample the Fourier space, which can take a long time. And the longer that you have a person inside of an MRI scanner, the more likely they are to move around, and that movement can introduce artifacts into the images. So then the question becomes like, how can you recover high resolution images if you subsample the Fourier space? So in order to reduce the scan time. So this is something that they've been working hard on at Neurospin. And one of the things that's been done.
You have 10
Sorry.
minutes.
Yep, sure. We're getting close to. One of the things that's been done is, so former PhD student, Lubna, looked at combining compressed sensing. So compressed sensing is the idea that you can use sparsity to help you recover high resolution or good quality images from a subsampled observation. And she combined that idea with parallel imaging in MRI, which generally can be quite challenging to reconstruct, but also requires some knowledge of the coils in your MRI scanner. So she's shown that using techniques like OSCAR, that you can recover pretty good features and beat other regularization techniques. And all of this, again, implemented through PySAP in this PySAP MRI plugin. And a very exciting thing is that another former PhD student at Neurospin has pioneered this new technique for sampling Fourier space called sparkling, which is kind of like an optimized Fourier sampling, which gives you pretty good resolution on the final images, but has a non-trivial reconstruction problem. So using PySAP, she's been able to reconstruct 3D data cubes of the brain at a fraction of the time that it would take to fully sample the Fourier space, which is pretty cool. So as I mentioned, that we said from galaxies to brains and beyond. So beyond, one of the things we're looking at is electron tomography. So there's a group in Grenoble, in CEA Grenoble, who are looking at basically reconstructing erbium-doped porous silicon. And don't ask me much about that. But you can see here that she has various different reconstructions of this sample, and again, implemented through PySAP eTomo plugin. So I hope that I've given you a little bit of, whetted your appetites a little bit for PySAP and how it could be useful. If you're interested in, dipping your toes into the pool, there's a PySAP tutorials repository where you can kind of get started playing around with some of the tools, particularly for MRI. There's something that we're looking to expand upon. But we'd be happy for any feedback. And just to finish off, I'll just leave you with some closing thoughts. So I just hope today that I've kind of sold what the point of PySAP is and how it's useful for the community, and certainly how it's a cross-disciplinary project. So, just in summary, that you have an inverse problem-solving toolbox that can be applied to virtually any problem. But we have specific applications in MRI astronomy and electron tomography. And we're very open for other people to contribute to this project. Moving forward, we aim to add more of what we have already, in particular, more tools for different problems. But also, we really want input from the community. And finally, one of the things that we're putting a lot of emphasis on is, speed. Because at the moment, a lot of these tools are very good for prototyping, but maybe for production might need some more work. So we're hoping to kind of add more GPU compliance and HPC updates so that it could be potentially used for production as well. So without that, I think that's all. I'll leave some time for questions, and thank you very much for your attention.
Thank you very much, Samuel, and thank you especially for leaving plenty of time for questions. That's great. We've got some questions in the Q&A chat, and if people want to ask questions live, please put your hand up. The first question in the Q&A I can see is from Andre. He's asking, the directory uses wavelets, but you could use other directories, correct? How tight is PySAP bound with wavelets?
Yeah, so in fact, any dictionary could be implemented, right? So this is one of the features in ModOpt, is that rather than defining a dictionary, we define what we call a linear operator. And that linear operator in principle can be anything you like. So you could in fact imagine even using something like deep learning to learn a transformation that is optimal for your problem, and then implement that transformation in the algorithm.
Cool. Next question is from Nico. If I would take a picture of the sky from my light-polluted backyard with a regular camera, could I then use PySAP to get rid of the noise from that light pollution?
Okay, well, I mean, I don't want to say conclusively yes, because I would have to kind of look into the problem a bit more. But in principle, I think all the tools are there, and the trick would probably figuring out how to define the right problem to solve that. But I would say that, like, in principle, it would be possible.
Of course, light pollution is also a question of background noise, right? So your signal to noise
Sure.
breakdown. Okay, next question is from Landman. Do you have parallel wavelet decompositions in PySAP?
What do you mean by parallel wavelet decompositions? Maybe.
I think it means parallelized.
Oh, parallelized. No, not at the moment. This is something that we're certainly working on.
All right. Last question I see is, what about non-linear models? For instance, if your detectors don't have a linear response.
Okay, so that one I don't think I can answer as easily. This maybe would be a better question for somebody else who has a bit more of a mathematical background on the team to answer, but I could certainly put that question to them.
All right, thank you. Are there any more questions? I don't see any hands raised, but this is your last chance to raise a hand and ask a question if you still. Okay, if not, then let's thank the speaker again.